This is a second session on NTFS fundamentals. As I mentioned in the first session, in NTFS, everything is a file. So all our system area that we had in FAT, all that's built into different files. And that's what we're going to go through here, is talk about those different files. And these are specifically referred to as metadata files. And most of them will begin with a $sign, so you can recognize them straightforward. But they are hidden files, so you have to specifically be looking for them, through some type of viewer editor to be able to locate them. And so here, through FTK Imager, we see in the root, we see an example of $, extend folder, attrib def, bad clus, bitmap, boot, so forth. Okay? So we're going to walk through these different metadata files. The most crucial one that we're going to be talking about, and we're going to be spending a lot of time in, is called $MFT, which stands for Master File Table. So this is a large database file, and every single file and directory has at least one record in the MFT, including the MFT itself. So one of the first entries will be about this database itself. Now, a file or directory can have more than one record, but they have to have at least one. And the MFT will take up about approximately 12.5% of the drive will be allocated up front for this database, so it can continue to grow, because you can't let it run out of space. But again, we'll get more detail as we go on about the MFT. The first 16 records are reserved for metadata files. So in this database, in the MFT, the first 16 rows essentially are reserved for either future use or for existing $sign files. There are 3 additional files in records 24, 25, and 26, again, that are also metadata files. Okay, so that's our MFT. Now we have what's called the MFT mirror, and this is a copy of the first 4 records in the MFT. So the first entries in the MFT are for the MFT itself, for the mirror, for a log file, and for the volume. These records, these first 4 records in the MFT, are backed up into a file called the MFT mirror, because these are the most critical files that need to have in order for the file system to be recognized. The $log file records all operations affecting the volume. So if this is changes affecting the partition itself, these actions are going to be recorded, and you can use this log file to roll back. Forensically, we can obtain information about creating, deleting, or moving new files. The $volume is the volume name. If you remember in FAT, when the volume name was just given a directory entry. Here it's a specific file that has the name of the volume, and this is where we find the version of NTFS. For some reason they put it in with the volume. And then there's something called the dirty flag. This is whether or not the system has been shut down properly or not. And so if on boot up, if the system is recognized that this dirty flag is set, it means it was not shut down properly, and it will want to run check disk against that drive on the next boot. The attribute def, this is a definitions file that contains all of the attributes of different types of, all the definitions of the different types of attributes that we have. Now again, these are not like the hidden read-only system files that we had in DOS. Here, everything is an attribute. So it's like your name, your address, your height, weight, hair color, eye color, all those things are attributes about you. Files have different attributes, and this defines all those different attributes. And this is the listing. So we have what are called the standard information attribute, attribute list, file name, object identifier, security descriptor, volume name, volume information, data, index root, and so forth. We'll be spending a lot of time on a few of these, including the standard information, the file name, and the data attribute. Those are going to be ones that we're going to look at a lot. Some of the other ones we'll review a little bit, but not to the same depth. Okay. The root directory is considered a file in here. It is a listing, again, all files and folders. And this is one of the ones that does not start with a $sign. This is one of the few that does not. It's represented by a backslash. But it is the dot that is the root. A $sign bitmap. This is an allocation state for each cluster on the volume. So this is very similar to the file allocation table. Remember our train cars. So we had a car listing for what the contents were for the file. So we knew car 3 pointed to 4, 4 pointed to 5. But if it had a number in it, that means it was allocated. And then in FAT, it also had a pointer. In a $sign bitmap, we don't use pointers. We just say whether or not they're allocated. And instead of being done at 4 bytes like we had in FAT32, we're doing this with 1 bit. So each bit represents a cluster. And 1 means it's allocated, 0 means it's unallocated. So here's our example. We have file 1 uses clusters 0 through 4. And again, clusters start counting at 0 instead of 2, like we saw in FAT. File 2 uses cluster 6 and 7. Cluster 3, file 3 uses cluster 8, 9, 10, 11, 12, 13, 14, 15. And file 4 uses cluster 16. So if we look down in this graphic down below, we will see cluster 0 is allocated. 1, 2, 3, and 4 all have 1s in it, because we see here clusters 0 through 4 are all associated with file 1, so they're all allocated. 6 and 7 are part of file 2. 6 and 7, we have nothing using 5, so it gets a 0. Okay. 8 through 15, all allocated, so it's all 1s. And then just 16 is allocated. So if we look at these, we can figure out what the hex code will be displayed. So this first one, we've got, if we look at the nibbles, it would be 8 plus 4 plus 1 is 13, that's a D. And then 8 plus 4 plus 2 plus 1 is 15, that's an F. And here we've got, again, all 1, so it's FF. And then this last byte, we just have a 1 in here, so it's 0, 1. So what we're going to see, if we looked at the $sign bitmap, the first 3 bytes would be DF, FF, 0, 1. And that would tell us which clusters, if we broke it down like what we see here, that would show which clusters are being allocated. So again, I can just kind of walk this through. So if I have file, I'll just say file 5 is using clusters, where we leave off at 16, so 17, 18, 19. Okay. So remember we had DF, so 1, 1, 0, 1, and then FF. So before 17, 18, and 19 were all 0s, now they're going to be 1s. So this first one was already a 1 because that was 16, 17, 18, 19. Now flip all over to 1s when we add this new file. Okay. Another thing to look at, if I give you, 3C as the byte that we look at, which clusters are going to be allocated. So if we write out the binary, 0, 0, 1, 1 for 3, and C is 12, so we have 1, 1, 0, 0. So this cluster is not allocated. This one is. This one is allocated, not allocated, not allocated. The next two are allocated, next two are allocated, and the last two are not allocated. So we would just have to figure out which bits these are representing for. So we can look that, and again, we'll get it more into the $ bitmap later on. But just recognize this is how that process is working. Okay. The $ boot is a volume boot record. This is going to start in sector 0 of the volume, not the physical drive, but the logical sector 0, just like we saw in FAT. This one can be up to 16 sectors in length. But most of the information that we're looking for is going to be in that first sector, and the same kind of information that we've looked at before, including, the number of sectors per cluster, total number of sectors in the volume, and the volume serial number. Okay, that information will still be in the volume boot record. We have a file called badclust. Now this works just like the $ bitmap, but the only time you ever flip a bit from 0 to 1 is when that cluster is marked as bad. So for some reason, if you're running check disk and it finds a bad area, it will go into that bitmap and mark that file or that cluster as a 1 and change that byte value. So most of the time they're going to be all zeros. $secure. Again, we're not going to spend much time on this. This has security descriptors for files. Upcase translates anything that you put in lowercase, translates it to uppercase, and vice versa. This is for searching. So when you type in a word, you can type it in either upper or lower or mixed case, and it will know how to properly search for all the different instances. $extend is a folder containing additional metadata files, including the object ID. This is a GUID. We've talked about GUIDs when we talked about GPT. So we get the file itself will get a GUID value. And again, we've talked about this. It's a 128-bit value, and the sequence in there is 4 bytes dash 2 bytes, 2 bytes, 2 bytes, 6 bytes, and it's little endian, little endian, little endian, big endian, big endian is our standard way of displaying that. Reparse points, this has to deal with setting up pointers. So you can take a folder and point it to another drive or to another volume. It also deals with hierarchical, I can never say that word, storage management systems. These are usually like tape volumes where you need to go out and find certain tapes out of a whole library of tapes. Reparse points will be used for that. And then something called $quota. This tracks user volume quota, so you could set that a user can only use 50 gig out of a 500 gig drive or whatever quotas, but this is rarely used. The USN journal. Journaling is very common in most file systems nowadays, used in Mac and Linux related file systems. And this keeps track of what's going on with the file system and keeps logs of that. So again, if you need to roll back or if something happens to the system, for some reason there's a system crash, then that information will be contained in the log file. NTFS is referred to as a lazy write system, which means it does not, as soon as you make a change, it does not instantly commit those changes to the hard drive. It keeps them in this journal, and then at some point it will commit that to the hard drive. So if a crash happens before it gets committed to the drive, when you restart it, it's going to want to go back and review those journal logs and implement those changes at a later point. So again, reviewing the metadata files. Forensically, we're really interested in the MFT is a big one that we're going to be looking at. The log files in USN journals, again, are becoming more and more forensically valuable as we're learning to parse through that information more. But again, we'll be stepping through this and just taking little chunks at it.